Alright, in this paper I'll be solving the 9709 Probability and Statistics 1, paper 55, May, June 2025. And for copyright reasons, I'll now be displaying the paper, so make sure you have a copy with you to follow along. And I just want to say before we get into the video, if you find the content that we make on this channel useful, please do subscribe. 81% of the viewers are not subscribed, and I can promise you that the more subscribers we have, the bigger we get, the more content we produce, the better the content you can expect to see here. So please subscribe. Question number 1. Two fair 6-sided dice with faces labeled 1, 2, 3, 4, 5, 6 are thrown. The two scores are noted. The random variable x is defined as follows. So we've got if the two scores are equal, then x is 0. If they're not equal, x is larger minus smaller score. So bigger minus smaller. And then part A, draw up the probability distribution table for x. So we need to figure out all the possible values that x can take up. And for us to do that, what we want to do is to draw what we call a possibility space diagram. So I'm going to put one die on the vertical axis and then the other die on the horizontal axis. So here I'll put die 1 and we'll put the other die, so the second die, on that axis. Each die has 1, 2, 3, 4, 5, 6. Those are the labels. And same goes for die 2, 1, 2, 3, 4, 5, and 6. Okay. So we're told that if the two scores are equal, then x has to be 0. So if die 1 shows a 1 and the other die shows a 1, then x has to be 0. Okay. And we can do that for when die 1 shows a 2 and die 2 shows a 2, that's going to be 0 as well. When die 1 shows a 3 and die 2 shows a 3, that's going to be 0 as well. Same goes for 4, 4, that will be 0, 5, 5, that will be 0, and 6, 6. So this whole diagonal is just 0. Okay. Let me move this 0 there. And that there. Alright, perfect. When they are not equal, the scores on either die are not equal, then it is the bigger score minus the smaller score. So if die 1 shows a 2 and die 2 shows a 1, it's 2 minus 1, so that's 1. If we have 3 and 1, it's 3 minus 1, then 4 minus 1, then 5 minus 1, then 6 minus 1. And we keep repeating it. If die 2 shows a 2 and die 1 shows a 1, then it's 2 minus 1. This becomes 3 minus 2, so 1, 4 minus 2, 5 minus 2, 6 minus 2, and we keep filling up our diagram. So 3 minus 1, 2, 1, that's 1, 2, 3, and then that's 3, 2, 1, 0, 1, and 2. And then that is 5 minus 1, so 4, 3, 2, 1, 0, 1, and then 5, 4, 3, 2, 1. The 0 should be up. Okay, and a 1 here. So that is our possibility space diagram. So inside the diagram, those are the possible values that x can take up. So x can either be 0, that's when the two scores are equal, or x can be 1, or x can be 2, 3, 4, or 5. So if we go to our table, if we draw up our table, And I have probability that x is x. So x can either be 0, 1, 2, 3, 4, or 5. Okay. What's the probability of getting a 0? We've got 1, 2, 3, 4, 5, 6. So 6 zeros out of a total of how many outcomes? So this is a 6 by 6 grid. So 6 times 6. So 6 out of 36. How many ones do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 10 out of 36. How many twos do we have? That's 1, 2, 3, 4, 5, 6, 7, 8. That's 8 out of 36. How many threes do we have? 1, 2, 3, 4, 5, 6. That is 6 out of 36. How many fours do we have? That's 1, 2, 3, 4. So 4 out of 36. And fives, we only have 1 and 2 out of 36. And double check that it all adds up to 1. So 6 plus 10, that's 16, plus 8, that's 24, plus 6, that's 30, plus 4, that's 34, plus 2, that's 36. And this is all over 36, so 1. Right, perfect. So that is our probability distribution table for x. Part B says find the expectation of x and the variance of x. So let's start with the expectation of x. If you go to the MF19, the formula for this under discrete random variables, you're going to get the summation of xp. And what this means is that I'm going to take my x multiplied by its probability, then add it to take my x multiplied by probability, then add it to the next and the next. So that's going to be our 0 times the 6 over 36 plus the 1 times the 10 over 36 plus the 2 times 8 over 36 plus the 3 times 6 over 36 plus the 4 times 4 over 36 plus the 5 times 2 over 36. And if we punch this into our trusty calculator, and we get 35 over 18. All right. And now the variance. So again, the formula is in the MF19. It's the summation of x squared p minus, in brackets, your expectation of x all squared. Okay. So we need to figure out what the summation of x squared p is. The expectation of x we already have. So summation of x squared p means take your x value, square it, multiply by its probability, then add it to your x value squared times its probability. So it's this whole expression, except now it's going to be a 0 squared, a 1 squared, a 2 squared, a 3 squared, a 4 squared there, and the 5, of course. So if we just do the summation of x squared p by itself, that's going to be 0 squared times the 6 over 36 plus the 1 squared times the 10 over 36 plus the 2 squared times the 8 over 36 plus the 3 squared times the 6 over 36 plus the 4 squared times the 4 over 36 plus the 5 squared times the 2 over 36. And what does this give us? That gives us 35 over 6. So our variance has to be the summation of x squared p, which is 35 over 6, minus our expectation of x squared. Our expectation of x is the 35 over 18, and this is O squared, So therefore, our variance has to be equal to, that's 35 over 6 minus the 35 over 18 squared, and that is 665 over 324, which is 2.05. And our expectation of x, we say that was 35 over 18, which is 1.94 to 3 significant figures. Right, so that is our final answer. On to question number 2. The heights of trees in a certain forest are classified as tall, medium, or small. The heights can be modeled by a normal distribution with mean 20 meters and variance or standard deviation 5 meters, so variance 5 squared. Trees with a height less than 14 meters are classified as small. So trees with a height less than 14 meters are classified as small. Okay. And then part A says, for 150 randomly chosen trees from this forest, how many would you expect to be classified as small? So let's start off by finding the probability of one tree being classified as small. Once we have that probability, we can just multiply it by the 150 trees and find how many of the 150 we'd expect to be classified as small. So the probability that H is less than 14, because that's the criteria for a small tree, and we standardize. So H becomes Z, and this is less than 14 minus the 20 divided by our standard deviation, which would be 5. So this becomes Z is less than, that is 14 minus 20 over 5, which is negative 1.2. I can write this as, I want to change it from negative to positive, so I can change the less than sign to a greater than sign. So this becomes positive 1.2. And I know that this is 1 minus phi of 1.2. 1 minus, I go to my tables, I read off phi of 1.2, that's 0.8849. And so therefore, this is not yet the final answer, because this is just for one tree, right? 1 minus 0.8849 is 0.1151. And then we have to, because this is the probability of one tree being classified as small, let's multiply that by 150 to find how many of those 150 we'd expect to be classified as small. So multiply that by 150, that is 17.265. And let's round up and say that we expect 18 trees to be classified as small. Now we are told that trees from this forest are classified as tall if their height is at least 8 meters. 25% of trees are classified as tall. Part B, find the value of H. So we're told that trees from this forest are classified as tall if their height is at least, so greater than or equal to, small h. Okay. And then we're told that 25% of the trees are classified as small. So probability of tall trees is equal to 0.25. And the criteria for a tree being tall is that. So that means the probability that the height is greater than or equal to h. This is equal to 0.25. And remember, under continuous distribution, greater than or equal to is the same as just greater than. So I can just drop this or equal to part. It won't make a difference. All right. And so what we can do is we know that H follows a normal distribution with all this good stuff. Oh, I didn't bring my bracket with me. We can standardize. So that big H becomes big Z is greater than our small h minus the 20 over our standard deviation, which is 5, and this is equal to 0.25. And then we can create a substitution, say let Z equal h minus 20 over 5, so that I can just write that as Z, right? This is all equal to 0.25. Now I want to draw a bell curve to interpret this. So I've got our nice bell curve. We know that this is centered at 0 since this is the standard normal. And we are saying that the area to the right of small z is 0.25. So that means our small z has to be somewhere here so that the area to its right is 25%. So it's 0.25. That means the unshaded area there has to be 1 minus 0.25, because remember the total area under the curve is 1. So this has to be 0.75. And so I know that my small z, I'm going to get that from finding the z value that corresponds to a probability of 0.25, but 0.25 is not in my tables, so I use the bigger value, 0.75, because they're both tied to the same z value. So if you go to your tables and you read off arc-phi of 0.75, you get 0.674. And so, because earlier we defined z as being h minus 20 over 5, I can say that 0.674 is equal to h minus 20 over 5. And now I can solve for h. So multiply both sides by 5. So that's 0.674 by 5. We've got 3.37 is equal to h minus 20. So h must be 20 plus 3.37. So h must be 23.37. If we want to round it off to 3 significant figures, h has to be 23.4. And that is our final answer. Question number 3. In a certain large school, on average, 2 pupils in 5 have music lessons. Okay, so 2 in 5 have music lessons. A random sample of 80 pupils from the school is chosen. Part A. Use an approximation to find the probability that fewer than 27 pupils have music lessons. Okay. So at AS level, the only approximation you will use is the normal approximation to the binomial distribution. So if any question asks you use an approximation, this is the approximation you should use. But it's always good practice to check if the conditions for that approximation are satisfied. In this case, let's define our random variable x as being the number of pupils who take music lessons. Number of pupils who have music lessons. So x here has to follow a binomial distribution, and we're looking at 80 pupils. Our success is them taking music lessons. So the probability of that's 2 in 5. And we're told to use an approximation. So I'm suspecting we have to use a normal approximation. Well, I'm not suspecting, I know, but just to check the conditions, we're going to check NP has to be greater than 5 and NQ has to be greater than 5. This is what we have to check. If these conditions are satisfied, then it is a normal approximation to the binomial. So our N is 80, our P is 2 over 5, our Q is going to be 1 minus P, so 1 minus 2 over 5, or 3 over 5. Factorize this as a decimal because it's easier to see. So that's 0.4, and 3 over 5 is 0.6. So NP is 80 times 0.4. And this is, what is 80 times 0.4? 32, which is greater than 5. And then NQ, so that's 80 times 0.6. That's 48, which is also greater than 5. So therefore, we can use a normal approximation. So use normal approximation to the binomial distribution. And so we can say that X approximately follows a normal distribution with mean NP and variance NPQ. So the mean of a binomial distribution and the variance of a binomial distribution. NP we already calculated to be 32. NPQ we still need to calculate that. NPQ is our 80 times the 0.4 times the 0.6, which gives us 19.2. And so that means X follows a normal distribution, and our NP we said that is 32. Our NPQ, that's 19.2. And now we can actually go back to the question and see what it is we need to solve for. So it says to find the probability that X, that fewer than 27 pupils have music lessons. Okay. Now remember that this problem was defined under discrete conditions under a binomial distribution. So now we have approximated a normal distribution, which is a continuous distribution. So that means we have to apply continuity correction. So this 27 under discrete conditions would have meant exactly 27, but under continuous conditions, it represents any number between 26.5 and 27.5. Okay, so if I say X is less than 27, I do not want to include any number within this interval. So to make sure of that, I need to say X is less than 26.5. So X is less than 26.5. That's our continuity correction. Now we can standardize and simplify as usual. So less than 26.5 minus our mean, which is the 32, divided by the square root of our variance. Punch this into your calculator. This is 26.5 minus 32 over the square root of 19.2. And that's less than negative 1.255. And again, I want to make this positive, so I have to flip the sign. It becomes greater than, and that's positive 1.255. I know I can write this as 1 minus phi of 1.255. And so this is 1 minus, if you go to your tables and you read off phi of 1.255, you're going to get 0.8953. And if we simplify this, that is 1 minus 0.8953, 0.105, correct to 3 significant figures. Now we are told that a random sample of 10 pupils, most of the times you see random sample of this many things is chosen. It's a binomial distribution. Random sample of 10 pupils from this school is now chosen. And then part B says find the probability that not more than 2 pupils have music lessons. All right. So let's define our random variable y as the number of students who have music lessons. Who have music lessons out of the 10 pupils who have music lessons. So I can say that y follows a binomial distribution and my n is 10. Probability of success Our success is a student having music lessons. That's 2 and 5. So that's going to be 2 over 5 or 0.4. And then the question says the probability that not more than 2. So not more than 2. That's a weird way to put it, but it means less than or equal to. At most 2. So less than or equal to 2. And now we need to find the probability of this. So if we say y is less than or equal to 2, we're looking at y is 0, 1, or 2. And we need to evaluate each of those. So we're going to do 10, choose 0 times 0.4 to the 0 times 0.6 to the 10. Hopefully you know that 10 choose 0 is 1. Anything to the power 0 is 1. So in reality here, from y equals 0, all we're interested in is the 0.6 to the 10 plus, now y equals 1, that's 10, choose 1 times 0.4 to the 1 times 0.6 to the 9 plus, we'll do the 2 now, 10 choose 2 times 0.4 to the 2 times 0.6 to the 8. Okay. And then let's punch this into the calculator. And this gives us 0.167 as our final answer. Question number 4. Students applying to Drydale College, what a name, take an entrance test. A student is either accepted or rejected or required to take another test with probabilities 0.3, 0.2, and 0.5 respectively. So we've got accepted, rejected, or take another test. So accepted is 0.3, rejected 0.2, and 0.5. When a student takes a second test, the outcomes and probabilities are exactly the same. So these probabilities here apply to both the first and the second test. Okay. Then we're told that a student who has to take a third test is accepted with probability 0.25 and rejected with probability 0.75. So for third test now, we're saying our acceptance is 0.25 and our rejection rate is 0.75. Okay, part A, draw a tree diagram to illustrate this information, showing all the probabilities. Okay. So when people take the first test, test 1, the entrance test, our rates, I should probably put this a bit low. Our rates are looking like this. We've got either you're accepted or you're rejected or you're required to take another test. The probability of you getting accepted is the 0.3 there, rejected 0.2, and another test is 0.5. If you're required to take another test, that's now test 2. You're either accepted, rejected, or you're required to take a third test. And we were told that the probability for the second test are the same as those for the first. So that is still 0.3, 0.2, and 0.5. Now, if you're accepted, then, well, you're done. If you're rejected, then you're done. If you're required to get a third test, this time you're either accepted or rejected. This is the last test they offer you. And the probabilities are 0.25 for acceptance and 0.75 for getting rejected. So that will be the tree diagram. It's a bit of a weird one. Part B says find the probability that a randomly chosen student who applies to Drydale College is accepted. Okay, so there's 3 ways you can get accepted into Drydale College. Either you just take, I should have labeled this test 3. Either you just take test 1 and get accepted, or you take test 1, then they tell you to take another test, and then you pass that second test. Or you take test 1 and they tell you to get another test, and you take the second test and they tell you to get another test, and then you're accepted on the third test. So those are the 3 ways in which you can get accepted to Drydale College. So probability of getting accepted is either you just take one test and you get immediately accepted, which is that, or you take test 1 and they tell you to take another test and then you get accepted on the second test. Or you take test 1, they tell you to take another test. You take test 2, they tell you to take another test, and then you get accepted on the third one. So let's evaluate each of those scenarios. So should probably not use A because now that makes it conflict with that. So I'll just write it all out. Probability of getting accepted. Accepted. So probability of getting accepted on test 1 is 0.3 plus take another test and then get accepted. So 0.5 times 0.3 or take another test, then take another test and then get accepted. So 0.5 times 0.5 times 0.25. So 0.5 times 0.5 times 0.25. And so if we punch this into the calculator, 41 over 80, or if you want to put it as a decimal, 0.5125. And that is our final answer. Part C says, find the probability that a randomly chosen student who applies to Drydale College takes at least 2 tests given that the student is accepted. So given is the key word. That means we're dealing with conditional probability. And we know that the formula for conditional probability says probability of B given A. This one's not provided in the MF19, so you have to memorize this one. Is equal to the intersection over the probability of the given event. So in our case, we are saying find the probability that a randomly chosen student who applies to Drydale College takes at least 2 tests. So at least 2 tests given the student is accepted. Okay. Given the student is accepted. So this is equal to the probability of the intersection. So that means they take at least 2 tests and they're accepted. At least 2 tests and are accepted. Divided by the probability of the given events of being accepted. Probability of accepted, we already calculated that in part B, so that's fine. We need to figure out the numerator. So they're saying you have to take at least 2 tests and get accepted. So if we go to our diagram here, there's 2 ways that can happen. I can either take test 1, then I'm told I should take another test, and then I take the second test and then I get accepted. So that's one way, because I've taken at least 2 tests and I was accepted. Or I could take test 1 and I'm told to take another test, and then I take test 2 and I'm told to take another test, and then I take test 3. So now I've taken 3 tests and I'm accepted on test 3. So either take 2 tests, get accepted, or take 3 tests and get accepted. So that becomes probability of TA, because test 1 and then accepted on test 2, or test 1, test 2, accepted on test 3. I'm sure we evaluated these probabilities. So that's this section here, which is this bit here. So this is equal to that bit. Okay. So if we simplify this, what is that equal to? 0.5 times 0.3 plus 0.5 times 0.5 times 0.25. That is 17 over 80 or 0.2125. And so our conditional probability, the probability of at least 2 tests, given that you're accepted, becomes the probability of at least 2 tests and accepted, which is this 0.2125, over the probability of being accepted in general, which is 0.5125. 0.5125. And if we punch that into the calculator, we get 17 over 41, right? Which is 0.415 as a decimal. And that is our final answer. Now we are told that 3 friends apply to Drydale College, but define the probability that all 3 are rejected. Let's just focus on one student for now. We want the probability that one student is rejected. We know that the probability of a single student being accepted is our 0.5125. If probability of accepted is 0.5125, if you're not accepted, then you must be rejected, right? So probability of rejected must be, it has to be 1 minus this, because probability of accepted plus rejected should add up to 1. So this has to be 1 minus 0.5125. So probability of a student being rejected is 0.5125. That's 0.4875. And so now there's 3 friends. So for friend 1, they've got a probability of 4.875 of being rejected. For friend 2, they've got a probability of 0.4875 of being rejected. And for friend 3, they've also got a probability of 0.4875 of being rejected. And so this has to be multiplied to each other, because I want friend 1 to get rejected and friend 2 to get rejected and friend 3 to get rejected. So 0.4875 cubed. And so therefore, that is 0.116, and that's the final answer. Question number 5. The Smarts and the Teasers are 2 quiz teams that each contain 11 members. Both complete a puzzle, and the following table gives the times taken in minutes by the members of each team. All right. Part A. Represent this information in a back-to-back stem and leaf diagram with Smarts on the left-hand side. Okay. So let's draw our stem and leaf. So I'm going to put Smarts on the left as instructed, and then Teasers have to be on the right. Then let's figure out what to do with our stem. So the smallest number I can see is a 9, and the largest number I can see looks like the 41. Okay. So I'm going to do 0, 1. Let's give it a bit of space, a bit of breathing room. 0, 1. Let's do 2, 3, and 4, right? And then our key here is going to say that if I've got 1, 2 here and a 3 there. This means that it's 12 for smarts and 13 for teasers. So key means 12, and in this case it's time, so 12 minutes for smarts and 13 minutes for teasers. And the key is very important. Don't forget to write a key for your stem and leaf diagram. All right. Now let's put our data in. So for 0, I only have 9, it seems, for smarts. So we've done the 9, and then we go to the 10s. So there is 11, 13, and 18. So 1, 2, 8, 11, 13, not 2. So that should be at 3, 11, 13, and 8. And 8, there's another 8. And in the 20s, we've got 22, 28, 29. 22, 28, 29. And in the 30s, I've got 30 and 38. So 0 and 8. And just the 40s remain, which is the 41. And let's do the same for our teasers. I don't have anything in the units. In the tens, I've got a 12, a 15, and an 18. A 12, a 15, and an 18. In the 20s, I've got 21, 25, 25. 21, 25, 25. And in the 30s, I've got 32, 36, 37, 32, 36, 37. Then I've got 39 and 39. So 9 and 9. And that's the stem and leaf diagram for 4 marks. Now we are told that for the teasers, so this is teasers, the lower quartile, that's Q1. Let me write it here. The lower quartile Q1 is 18. The median Q2 is 25 minutes. And the upper quartile Q3 is 37. Okay. On a single diagram, draw box and whisker plots for the 2 teams. All right. So we are going to have one axis here, and our axis is going to represent what are we measuring? It is time. And what's our unit? In minutes. Okay. So there are 5 things that you need to be able to draw a box and whisker plot. And that's your minimum value, your Q1, your Q2, your Q3, and your maximum value. All right. So for the teasers, we've already been given Q1, Q2, Q3. We just need to figure out what our minimum value is and what our maximum value is. So minimum value, that's the smallest value, which is the 12. And the maximum value is the largest value, which is the 39. And now we need these same 5 values for, what's the name of our other team? Smart. Yes, we need the same 5 values, but for smarts. So we need a minimum value, we need a Q1, we need a Q2, we need a Q3, and we need a maximum value. Okay. So let's do that. I think let's start by just finding the minimum and the maximum, right? Because those are easier to get. Minimum value is gonna be the 9 here, and the maximum value is gonna be the 41. 41. Then we need Q1, Q2, and Q3. So Q1 is lower quartile. First, we need to figure out the position of our lower quartile, right? The position of Q1. That's going to be, how many data points do we have? How many members for Team Smarts? Team Smarts has 11 members. So to get our lower quartile, it's a quarter of n plus 1. Our n is 11. So quarter of 11 plus 1. 11 plus 1 is 12. So quarter of 12, which is 4. So the number in position 4 becomes our Q1. So read from right to left. So 1, 2, 3, 4. The 18 there becomes our Q1. For the Q2 position, it's going to be a half of n plus 1. So half of 12, which is 6. So the 8 is in position 4. So this has to be position 5. And this is 6. So that becomes 22 is our median. 22. And now we also need Q3 to get the position of our upper quartile, Q3. It's going to be 3 quarters of n plus 1. So 3 quarters of 12, which is 9. We know that this 2 here is in position 6. So 7, 8, 9 has to be the 30 as Q3. Okay. So those are the 5 values that we need. Once we have these, we can draw our box and whisker plots. Let me just move them to the side so that they're not in the way. All right. Okay. Perfect. So I think we're gonna move in tens. I'm gonna mark this as 0 and then go 10 and I'll go 20 and I'll go 30 and I'll go 40 would have to be somewhere here, and then 50. Okay, but pick whatever scale is appropriate for your grid. All right, so let's start with smarts. So the minimum for smarts is at 9. 9 would be just less than 10. So somewhere there. And then Q1 is at 18. So 18, just less than 20. And then Q2 is at 22, so just over 20. And then Q3 is at 30, so bang on at 30. And then our maximum point is at 41, so just slightly over 40. And now the box, join your lower and upper quarter, and then go all the way to the maximum and all the way to the minimum for your whiskers. And this is for smart. Then on top, we want to do the teasers. So their minimum point is at 12. So 12 would be somewhere here. And then we're going to go to 18 for the Q1. So 18. Oh, they share the same Q1. So I need to put 18 here. And then we need to go to 25. So 25 would have to be somewhere here. And then we need to go to Q3 at 37. So 37 is here. And then our maximum point, our maximum value is at 39 for the teasers. So 39 is just less than 40. So somewhere here. and draw the box. So connect your upper and lower quartile, and then the whiskers. Okay, and label this. This is for the teasers. All right, so that's your box and whisker plot. Now the part C says, make two comparisons between the times for the two teams. So when they ask for two comparisons, you need to compare two things. The central tendency, where is most of the data located, and the spread, how spread out is the data. So let's start with the central tendency. We can tell that on average, right, the teasers, they take more time, clearly, because the median, if you just focus on the median, the teasers, in the context of this is time taken to solve a puzzle. So on average, we can tell that the teasers spend more time completing the puzzle, whereas the smarts are quicker because of the smaller median. So we can say smarts take less time or smarts are quicker. Since they have a lower median, smarts are quicker than teasers. Teasers, since they have a lower median, i.e., the median for smarts is 22, and that of teasers is 25. So 22 versus 25. This is one comparison, and it deals with how spread out. Rather, it deals with the central tendency of the data, right? So remember, your measures of central tendency are mean, median, and mode. So here we're using the median to explain our central tendency. Then you need to explain the spread. And so the spread is explained by your variance, standard deviation, your range. And in this case, we actually want to use interquartile range. So the box that you can see, or not box, but a rectangle. Should be like a rectangle and whisker plot. Don't know why it's called a box, but yeah. This rectangle, the bigger the rectangle, the more spread out the times. So in this case, we can say that the times for teasers are more spread out. Are more spread out. Are more spread out than those of smarts. Than those for smarts. Since interquartile range for teasers is bigger. So i.e., what's the interquartile range for the teasers? It's Q3 minus Q1, so that's 7 plus 10 plus 2, that's 19. And we're comparing this to the smarts interquartile range, which is 30 minus 18, so 12. And these are the two comparisons. So that's that for question 5. Let's go on to question number 6. So we are told that a dance club has 12 members made up of 7 men and 5 women. Every Monday, a team of 4 is chosen at random to represent the club in a competition. Part A. Find the probability that on a particular Monday, the team consists of 1 man and 3 women. Okay. So we want to pick a team of 4, and we've got 3 slots. One of the slots we're giving it to the men, and the other slot is going to the women. So in how many different ways can we do this? We've got 7 men and we want to pick 1. We've got 5 women and we want to pick 3. So that is 7 choose 1 man and 5 choose 3 women. This is the total number of different ways in which we can pick a team of 4 consisting of 1 man and 3 women. So that would give us 70, right? But they want a probability. So for probability, it's going to be equal to the probability of, let me write it as probability of 1 man and 3 women, 1 M and 3 W is equal to, so the number of selections given this restriction over when there are no restrictions. So over the total possible way we can select 4 people without any restrictions. So if we are not worried about the ratios of men and women, then we just look at these 7 men and 5 women as 12 people. And we're saying from the 12, we want to pick 4. Right, so this is over 12 choose 4. And so this ends up being 70 divided by 12 choose 4. That is 14 over 99. Let's go on to the next one. Every Tuesday, the darts club chooses 3 teams of 4. Each team enters a competition in a different town. In how many different ways can the teams be chosen if there are no restrictions? Okay. So we've got our 12 members, right? We've got our 12 members and there are no restrictions here. So I don't care how many of these are men and how many are women. And I want to pick 3 teams of 4. So I've got my first team here. And then I want my second team of 4. And then I want my third team of 4. So in the first team, in team 1, I've got 4 slots and I'm choosing from 12. So I'm going to say 12 choose 4. But once I've put 4 people into team 1, I can only select from the remaining 8 people. So in team 2, I've got 8 to pick from and I want to choose 4. Once I've selected team 2, I've put 4 in here and I've put 4 in there. So only 4 people remain and they all have to go into team 3. So 4 choose 4. And so this all simplifies down to 12 choose 4 times 8 choose 4 times 4 choose 4, 34,650. Part C. In how many different ways can the teams be chosen if each team must contain at least 1 man and at least 1 woman? Okay. So, all right, so now it matters. We've got the 12 members. And in the beginning, we were told that 7 of these 12 members are men and 5 are women. So I need those ratios here. And now we've got our 4 teams. So team 1, and I've got team 2, and I've got my team 3. And I'm told that I have to put at least 1 man in here and at least 1 woman in here, at least 1 man in here, and at least 1 woman in here, at least 1 man in here, and at least 1 woman in there. So what we're going to do is that we want to write down all the possible scenarios we could have that satisfy this condition. So I could put, let's put 3 men in the first team. So we end up with 1 woman. And let's put, remember we've got a total of 7 men. So now I've got 1, 2, 3, 4, 5. I only have 2 men left. So I must put 1. I could put 2 in here. And then the rest has to be filled up by women, right? Because now I've got 1 man, 2, 3, 4, 5, 6, 7, right? And so that means I have to have women in this team. And all 3 of these teams satisfy the condition of at least 1 man and at least 1 woman. In fact, I think it's easier if we write it as the first team has 3 men and 1 woman. The second team here has 3 men and again 1 woman. The fourth team here has 1 man and 3 women. Okay. So this is the first scenario that we could have. And so keep in mind that this team 1 is going to some different town, let's call it T1, and this team 2 is going to another different town, T2, and then this team here is going to town 3. Okay, so I don't really care the order in which the men are in because I'm just trying to select a group of men and women, right? So even if I rewrite this as MMMW, it's the same thing. So this is a combination. But what matters is that I could swap these around. I could swap 1 man and 3 women and say, let the 1 man and 3 women go to town 1 instead. So I could have 1 man and 3 women, and then I could have 3 men, 1 woman, and then 3 men, 1 woman. So now I've changed the groups, I've changed the towns which each group is going to. So now I've got this group of people going to town 1, and this group of people going to town 2, and this group of people going to town 3. So I also need to account for the possibility of that happening. So how many ways can I swap around where each of these teams is going, where each of these groups is going? So I could do the 1 man, 3 women. Notice that 3 men, 1 woman is the same as 3 men, 1 woman. So this would be the same thing, right? Even if I swap these two, it's exactly the same thing. It's not going to change anything. Alternatively, I could also just move this 1 man, 3 women to team 2, 1 man, 3 women, and then do 3 men, 1 woman, 3 men, 1 woman. That's another possibility. So instead of trying to find the number of different ways for each of these different scenarios, I can just calculate for the first scenario and multiply it by 3, because I know that I can pretty much here what we're focused on is this team here, because that's the only different one. I know that I can send the 1 man and 3 women to any of the 3 towns. They don't have to specifically go to town 3. They could be in town 2 or town 1. So I have to account for that by multiplying by 3. All right, so this would be scenario 1. But we know that at the end of scenario 1, I'm going to have to multiply it by 3. We'll come back and evaluate this. Alternatively, I could have said, right, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. I need at least 1 man, 1 woman, 1 man, 1 woman, 1 man, 1 woman. I can put 2 men in the first group, 2 men in the second group. And so I've used up 1, 2, 3, 4. I've got 5 men, so I need 2 more men to make 7. And so we have to fill the rest with W's. Okay, so this now becomes 2 men and 2 women. Excuse me. And this is 2 men and 2 women as well. And the last scenario is 3 men and 1 woman. So now I'm sending 2 men, 2 women to town 1, 2 men, 2 women to town 2, 3 men, 1 woman to town 3. But it doesn't have to be that way. Any of these groups could go to either town. So to take into account for that, I know that I can also rewrite this as 3 men, 1 woman, 2m, 2 women, 2m, 2 women. Again, these would be exactly the same thing, 2 men, 2 women. It's the same ratio of men and women, because that's what we're interested in here, right? So that would be the same, or I can just move this 3 men, 1 woman group to the middle. And then I have 2 men, 2 women, 2 men, 2 women. And so these are the 3 different scenarios that come up here. But like we explained earlier, I can just find the number of different selections for the first one and then just multiply by 3 instead of doing the individual calculations. All right. So now let's let's evaluate this. Let me remove that. So 3 men and 1 woman. So I want to pick 3 men from 7. So 7 choose 3 times. I want to pick 1 woman from 5. So 5 choose 1. When I get to the second team, I've already picked 3 men. So I only have 4 more to pick from. So it becomes 4 choose 3 times. I've already picked 1 woman. So I have 4 to pick from and I want 1. And when we get to the last group, it's going to be, I've picked 3 and 3 men. So I've picked 6 men. So I only have 1 to pick from and I want 1. And then I've picked 1 and 2 women. So I only have 3 to pick from and I also want to pick 3. And we said, oh, this has to be multiplied by 3. So what does that give us? That is 7 choose 3 times 5 choose 1 times 4 choose 3 times 4 choose 1 times 1 choose 1 times 3 choose 3 times 3, which is 8,400. And then let's do this second scenario here. So 2 men. I want to pick 2 men from 7, so 7 choose 2. And I want to pick 2 women from 5, so 5 choose 2. Multiplied by, I've picked 2 men, so I only have 5 left, and I want to pick 2. I've picked 2 women, so I only have 3 left, and I want to pick 2. And now I've picked 2, 2, so I've picked 4 men. Now I want to pick 3, and I'm picking from 3. I've picked 4 women, so I only have 1 to pick from, and I want to pick 1. All of this is being multiplied by 3. And so that is 7 choose 2 times 5 choose 2 times 5 choose 2 times 3 choose 2 times 3 choose 3 times 1 choose 1 times 3, which is 18,900. Okay, and so we said either we've got this first scenario or we've got the second scenario. So and or, that means I have to add these two numbers, right? So 8,400 plus 18,900. What does that give us? That is 27,300. And that's the final answer. Now we're given that the 7 men stand in a line for a photograph. 2 of them are brothers, George and Harry. Part D, how many different arrangements are there of the 7 men in which there are exactly 2 men between George and Harry? Okay, so we've got, let's put George and Harry, and I need 2 men in between. So 1, 2, 3, 4. So I have 3 men remaining. So I'll call this M1, M2, M3, M4, and M5. Okay, so there's our 7 men in a line. So how we want to do this is first find the number of different arrangements of the blue men, right? The 5 blue men. Completely ignore George and Harry for now. And how many different ways can we arrange the blue men? It's going to be 5 factorial. Now we're going to take into consideration George and Harry. Alternatively, I could have had a situation like this. 1, 2, 1, 2, 3, 4, 5. Okay. And then I've got George and Harry here. Or I could have 1, 2, 1, 2, 1. And I could have George and Harry here. Or I could have 1, 2, 3, 1, 2. And then George and Harry. Okay. So for each of these scenarios, the calculation would have just been 5 factorial, right? Because in this scenario, assuming George and Harry are fixed in position, I'm just arranging 5 other letters. In this scenario, assuming George and Harry are fixed in this position, I'm just arranging 5 other letters, which is 5 factorial again. So we can just say that this is 5 factorial multiplied by the number of scenarios we have, right? So in this case, that's 1, 2, 3, 4. So 5 factorial multiplied by 4. But one thing we also have to take into consideration, they just say that there have to be exactly 2 men in between George and Harry. They didn't say that George must be first in line. So it can be flipped, right? We could have Harry coming first and then George coming second. So we could have something of the sort. 1, 2, 1, 2, 3, right? For all of these 4 scenarios. So that means this here is the total number of arrangements for the 4 scenarios, and I just have to double that because it can be flipped, because Harry can come before George in all 4 of those scenarios. So I can multiply this by 2. And so that is 5 factorial by 4 by 2, and that is 960. And that is the final answer. All right. And that also happens to be the paper. If you like the way that I break down these questions and you find that you're struggling with AS and or A-level maths, then you can sign up for tutoring using the first link in the description down below. Otherwise, thank you for watching. I hope this video was helpful, and if it was, please share it with your friends and anyone else who you think might benefit from this. Like the video, subscribe, and I'll see you in the next one. Goodbye.